Okay guys, let's begin. So, sorry for my delay in getting over here, getting a couple of kids set up for tests and, new different space. So this is where we are today. Good on you coming in. We're cranking out revision of chapter 3, which was the applications of calculus unit. And this is a fat unit, like there's a lot of stuff to go through in here. I've put it down to 5 questions. So we're covering all the key skills. We'll look at using our calculator to help us out. I'll probably just go from Desmos rather than the calculator. How we can use graphs and so forth and all that kind of stuff. So let's get straight into it. So the first thing we've got is equations of tangents and normals. So we have the function y equals 2 on top of x squared. And we want to find the tangent at x is 1 and y at minus 1 and y is positive 2. So for a tangent, what we're talking about is a line that's parallel to the slope, parallel to the curve at that point. So just try and find a good marker. So we know the equation of a line is y equals mx plus c. So that means for the line, we're going to need to know the slope and the y-intercept. So for a tangent, there's 2 things we need. The point of contact, which we're given. All right, occasionally you'll just be given an x value. Sometimes you're just given a y value, but given a coordinate, you can find the other one just by putting it into the equation. And then we need the slope. They're the 2 things we need for a tangent or for a normal. We need the point of contact and we need the slope. Now, if this is the function, okay, that's the function. We need the slope function. We need the derivative. So we've got y is 2x to the minus 2. That's one way we can express it, which means the derivative would be minus 4x to the minus 3. That's the derivative function. It can be expressed like this. And we want to know the slope when x is minus 1. When x is minus 1, we want to know what's the slope. This is the slope function, tells us the slope for any value of x. And we can put all this straight in our calculator. We'll have minus 4 on top of minus 1, we'll have positive 4. X is minus 1, y is 2. Okay, so that's the point where we're drawing the tangent, right? This is where we're drawing it, when x is minus 1, y is 2. Now, one thing you'll remember from your calculator is if you graph this function and you trace along to that coordinate and you have the derivative setting on, it will tell you the x value, the y value, and the slope at that point. So you can get all of those pieces of information straight off the graph, just by solving, tracing along. Okay? So we got the slope. And now all we're doing is finding the equation of a line that has a slope of 4 and passes through this point. So we're going to have y equals 4x plus c. And then we'll go when x is minus 1, y is positive 2. Plug both of those in. X plus 6. And so if I sketch that line, okay, you can see tangent touching the curve parallel at that point. All right, there's lots of different ways of doing a tangent. You can do the formula, you can do general form. I like to just think about it using an intuitive process. We need the equation of a line that passes through that point. That's parallel at that point, has a slope of. Okay, good. Let's move on to the next one then. And in exercise 3B, 3C, and 3D, we did all of these over successive lessons, but it's really consolidated in 3D question 4, where they ask you to recap all of the skills that you learned. So we're using calculus techniques to talk about when a function is increasing and decreasing, when it has stationary points, and when it has points of inflection. So I'm going to sketch the function. We'll just talk about it first. So we've got the function x to the power of 3. I'm going to call it y equals x to the power of 3 take 3x squared. Okay. So if we're looking at the function, what you can see is if you were to walk along, you'd be walking uphill. So the function is increasing until we get to 0, and then it is decreasing. You'd be walking downhill until we get to positive 2, and then it is increasing again. So you can see where it's increasing and decreasing from the graph. We can also see it's concave down until we get to about here, and then there's a point of inflection there, and it changes to be concave up. All right, so there's a point of inflection there, and our stationary points occurring here and here. Those are the turning points where the slope is stationary. Okay, so for part A, find when the function is increasing and decreasing. So our function is x to the 3 take 3x squared. So the derivative function then is 3x squared take 6x. Now, if it's increasing and decreasing, all that means in terms of calculus is it has positive slope, all right, or negative slope. So if this is the slope function, we just want to know when is this function positive, above the x-axis, when is this function negative, when is it below the x-axis. And so we do that by drawing the sine diagram, right? So let's do a manual sine diagram here. If we want to find the roots, we make it equal to 0. What can we factorize? 3x, we can pull out the front. So we've got 3x times x take 2. Apply the null factor law. And so we've got 2 roots on this quadratic, 0 and 2. We have a positive a value, which means it opens upward. Okay, so that means it's going like this. So all of that we can do manually, or you can just sketch it. You don't even have to type in the, what's this? You don't even have to type in the function. What about, can I do this? How do I do it? Sketch. Alright, let's change this to f of x. And let's sketch f dash of x. Alright, you can do that in your calculator as well. You can press graph the derivative of the first function. And you can see from the sine diagram, right? Positive, negative, positive. Okay, so now let's answer the question. Where is the original function increasing and decreasing? Right? Remember, we're not looking at this one going, oh, it's going down and it's going, no. We're talking about the original function. We're using the derivative function to make statements about the original function. And so we can see increasing for x is less than or equal to 0 and x is greater than or equal to 2, and decreasing 0 to 2. Alright, now we can actually see that just from the original graph. Increasing until we get to 0, decreasing between 0 and 2, and then increasing again. Okay, the other thing, so that's part A done. Part B says, how about the stationary points? Well, we can see from this sine diagram, the slope is 0. That means the function is stationary, it's horizontal. At x is 0 and at x is 2. So we have stationary points at x is 0 and x is 2. And we can just find their nature from the graph. We have a local max at 0, 0, and a local min at x is 2, and the y value minus 4. Very good. Okay, intervals when it's concave up and concave down. So, the function is concave up and concave down. And we base that off of the sine diagram of the second derivative. So this is the first derivative, right? So that means my second derivative is going to be 6x take 6. Okay, if we want to draw the sine diagram of this one, let's just do it straight from our calculator this time. Okay, so don't confuse you. Let's just draw the f dash dash of x function. All right, and we can see what's its root. G solve the root. Its root is 1. Okay, here's 1, and it's below the x-axis, and then it's above the x-axis. All right, so we can get that sine diagram straight from the graph. This is the f dash dash of x sine diagram. And what this tells us about the original function. Concave down when it's negative, concave up when it's positive. So our function then, our original function is concave down for x is less than or equal to 1, and concave up for x is greater than or equal to 1. Now, we've said as well, concave down, okay, you can think of it like a cave. Concave up, some people call convex, okay? So convex and concave up mean the same thing. Sace's notation is concave up, all right? You may see convex pop up in old papers. Okay, so that's that one. Last one, points of inflection. Points of inflection occur when the second derivative equals 0 and the sine diagram changes sign. Okay, so the second derivative is 0 when x is 1, and we can see the sine diagram changes sign. All right, now this, remember there's 2 types of points of inflection. This one is non-stationary because this root does not also appear here. If they have a root in common, then it's going to be a stationary point of inflection, but this root only appears on the second derivative. So we have non-stationary inflection at, and we've got x is 1. And when x is 1, y is 2. Net minus 2. Okay, so that's like, what are we doing in 3D, 3C, and 3D? We're using calculus techniques. We're using sine diagrams of the second derivative and the first derivative to tell us about the original function. All information we can get from the graph anyway. All right, any questions about that? All right, let's move on to the kinematics question then. So, I'll clear a bit of space. All right, what have we got? Displacement function, 12t take 2t to the power of 3 take 1. Find the velocity and acceleration. Oh, my battery's going low. That's all good. We might just have to use that calculator. All right, that's our S of t function. Find velocity and acceleration. Okay, so velocity is the first derivative, acceleration is the second derivative, right? Take 6t squared, and acceleration is going to be minus 12t. Very good. Find the initial conditions and interpret their meaning. Okay, so S of 0, when time is 0, the displacement is going to be minus 1. And what's our units? We've got centimetres. So the initial position of the particle is 1 centimetre to the left. V of 0. All right. 12 centimetres per second. Initially moving to the right at 12 centimetres per second. And A of 0 is 0. So its velocity is not changing. All right. It's not accelerating when time is 0. So that's part A. Part B Right, C. Find the time and position when the particle reverses direction. Okay, it's going to reverse direction when the velocity sign diagram changes sign. So we need to draw the sign diagram of this. Now, again, we can go straight off our calculator, or we can do it manually. If we have 12 take 6t squared is 0, we have 6t squared is 12, t squared is 2, and then t is the square root of 2, plus or minus. So what that means, these are the solutions, right? However, when we're considering kinematics, we only consider positive values of time. So we don't need to consider the negative solution. We only consider positive values of time. Now, it's a quadratic and it's got a negative a value. The coefficient of the squared term is negative, which means it would be opening downwards. So it means it would go like this. It would be negative, positive, negative. All right, again, we can get that straight from the graph of this equation. So there's the sign diagram of it. And it says, find the time and position when the particle reverses direction. Well, it changes direction when time is root 2. And it changes direction because we have positive velocity, which means we're moving to the right, and then we have negative velocity, which means we're moving to the left, and here the velocity is 0. All right, when time is root 2, what's that, 1.4? The velocity is 0. All right, so to answer this part, changes direction at t equals root 2. If it wants the position when time is root 2, you're finding s of root 2. You put root 2 into the displacement function. All right, which we'll have to do in a moment to draw the motion diagram. So I'm just going to leave that for now. We can come back and scribble that part in a sec. Okay, when is the particle's speed increasing? All right, speed is increasing when velocity and acceleration have the same sign. Now, if we draw the sign diagram for acceleration, so this is the velocity sign diagram, and I'll draw the acceleration one just underneath it. All right, now this is the equation of a line. It has negative slope and it has a y-intercept of 0, so it's like this. Okay, so that means when do they both have the same sign? Well, they both have the same sign when time is greater than root 2. So to answer, speed is increasing, t is greater than root 2. Okay, how about when is velocity increasing? Velocity is increasing when acceleration is positive, and acceleration is never positive. So what's that? Part 2, that's part 1, part 2, never. Okay, never because the acceleration function is never positive for positive values of time. Okay, last one. Draw a motion diagram for the particle. So for a motion diagram, we need initial position, we need position where it changes direction, and then we need final position. So we might just do it over the first 3 seconds. We're not given a constraint. Has anyone calculated s of root 2? Traces. So our function is (12x) take 2x to the 3, take 1. And we're talking about x equals square root 2. 10.314. And then x is positive 3. Intersection, minus 19. Okay, so as far as the motion diagram goes, you can see we go from minus 19, that's the point furthest to the left, to positive 10.314, that's the point furthest to the right, So I just go, here's 11, here's minus 19, here's minus 1. We start at minus 1. We're initially moving to the right. We have positive velocity. We get to the point 10.314. I'll just move that over a little bit. There's 11. And then we 10.314. And then we go back the other way after 3 seconds. So here's time is 0. Here's time is root 2. And here is time is 3. Alright, to work out the total distance, you know, we could go 10.314 plus 10.314 plus 19. Sorry, that's going to be 11.314 because we're 1 plus 10.314. Alright, everyone okay with that one? Good, recap of kinematics. Okay, the height of Pinus radiata. So these are an American tree and we grow them here because they grow tall and straight. 20 take 97.5 on top of T plus 5. Okay, the height of Pinus radiata is given by this equation. T is the number of years after the tree was planted from an established seedling. How high was the tree when it was planted? So, what's the height when time is 0? Alright, so we can solve it by typing it in here or just by graphing it and going straight off your calculator. Now for this one here, maybe we'll just use our calculator for all of these answers because we've got a few answers to come up with. Let's see if I can beat it. Apologise. 20 take 19.97.5 on top of x plus 5. Okay, now we want to know when x is 0, the y-intercept, 0.5. So h of 0 is 0.5 metres tall. Okay, part B. Find the height of the tree after 4 years, 8 years and 12 years. Okay, let's just do B part 1. That's when the time is 4. How tall is the tree? Alright, so I'll just type in x is 4. What's the y value? And I've got 9.167. Okay, you do the same for 8 and 12. Let's move on to part C. Find the rate at which the tree is growing when time is 0, 5 and 10. Okay, so here, if you've got your calculator and you're tracing along it, it's going to tell you the slope at those points. It's going to say dy on dx's. That's what we're after. I don't have that function up here on Desmos, so instead I'm just going to graph the derivative.